Welcome to springlib.
So once again, welcome to a new problem. We still have a diffraction grading. We have a diffraction grading, and our goal in this problem is to find our D, which is the, so we have to find two things. First thing we want to find is the slit separation. So slit separation is this gap right here. That's D. That's the slit separation. And the next thing we want to find out in this problem is A, which is the slit width. These are two items. We have a mixture, so light is coming in with two wavelengths. The first one, lambda 1, is 500 nanometers. The second one, lambda 2, is 600 nanometers. And they're moving perpendicular to the grating. The grating itself, this distance, L, is the length of the grating, and the number of lines, N, is the number of lines coming in. So assume this is lambda 1, 2, it's a mixture, it's a unique wavelength, which is a mixture, and our goal is to find D and A. And on top of that, we also want to find the biggest order of maxima you get from the grading. So those are things you're dealing with. One of the assumptions is that if the light is coming in like that, it's gonna disperse that way with an angle of theta. Theta is assumed to be less than or equal to 30. So the first and second max of the wavelengths of lambdas show up when this is true. So when theta is less than or equal to 30, that's when the lambdas show up. So we're just going to go ahead and jump right into the problem. And the first part we're seeing is d sine theta equals to m lambda. Remember, we had two wavelengths. Lambda 1 is 500 nanometers and lambda 2 is 600 nanometers. Those are the two wavelengths we had. The assumption is that the angle is less than 30. So it follows that if this is true, we can divide both sides by d, and so sine theta equals to m lambda over d. Or we can flip it and say m lambda over d equals to sine theta, but sine theta is less than sine 30, so it follows that m lambda all over d has to be less than or equal to sine of 30. So this is lambda 1, 2. If you can recall, it's a mixed wavelength. Multiply both sides by d, we get to see that m lambda, the mixed wavelength, is less than or equal to d sine 30. Alternatively, you could see that as d sine 30 being greater than or equal to m times the mixed wavelength. If you flip it, you get 1 over d is less than or equal to sine 30. All over m lambda 1, 2, which is a mixed wavelength. Recall the relationship between the number of lines, n, and the length together with the separation, meaning that the number of lines is inversely proportional to the separation. If you increase the separation, then you're decreasing, or rather, if you increase the number of lines, you're decreasing the separation. And so looking at the equation, we can see that there's an inverse relationship. The resolving power is therefore proportional to the number of lines. And so we want to maximize this dispersion, or the resolving power. We want to maximize that. So if we maximize n, then 1 over d will also be a maxima. And for that to happen, is you see that since 1 over d is a maxima, and we had 1 over d is less than or equal to sine 30 m lambda 1, 2. So we had a choice. Do we take less than, or do we take the equal to? We take the equal to because we want to maximize 1 over d. Why is the 1 over d maximized? Is because we want to maximize the resolving power. That's one of the goals of the problem. We want to maximize the resolving power. So then 1 over d has to equal m lambda 1, 2 over sine of 30. So we take the equal one and we ignore the less than, because our goal is to maximize. So we can now comfortably solve for d and see that d is sine 30 over m, the mixed lambda at maxima. M equals to 2, the order is 2, and lambda 2 is 600 nanometers. So that's when the max separation happens. And these two conditions are met. So d is sine of 30, m is, d is, well, this one we had to, it's the other way around. So we had sine 30 in the denominator. We had sine 30 in the denominator, and then we had m lambda 1, 2 in the numerator. So d becomes twice, change the 600 to meters, 600 nanometers to meters. That's 10 to the 9th power nanometers. We divide both sides by sine of 30, or rather the denominator by sine of 30. So our separation d becomes 2.40 times 10 to the negative 6 meters. That's our separation. So that's the initial part of the problem. The second part of the problem, we understand that d sine theta equals to lambda 2 and a sine theta equals to m2 lambda 2. So m2 has to equal d over a, and we're going to plug in the specific numbers. Remember, we solved for d, 10 to the negative 6 meters. And then, of course, a is 3. And the reason why we have to solve for, we have to come back. This is not m2, this is a, sorry. So a, using that equation, a has to be d over m2. That's what we're saying. It's the value of a. So this one, m2 is going to be 3. And the reason why we're making m2 to be 3 is because the smallest slit separation happens when m equals to 3. So then if you simplify this problem, you get to see that a becomes equivalent to 8.00 times 10 to the negative 7 meters. 8.00 times 10 to the negative 7 meters. Of course, the final part of the problem, we want to find the maximum order. And so the maximum order happens when sine theta equals to 1. If you recall the sinusoidal shape of a sine graph, when y is sine theta and the angle is theta, this value of sine theta is 1. So to maximize m max, you use d over lambda, and the reason why we use d over lambda is because if you can recall, d sine theta equals to m lambda. So then you divide both sides by lambda like that. These two cancel. So m is d over lambda sine theta. But then sine theta is 1 when we maximize the order. So this is 1. So the maxima order happens when we have d over lambda. We can plug in the values. D was 2.40 times 10 to the negative 6 meters, if you can recall. And lambda, or wavelength, was 800 times 800 times 10 to the negative 9, if you can recall. So this is an extended, so 800 times 10 to the 9, that's our lambda. So 800 times 10 to the negative 9 meters. And so our final step, we're going to get 3, but we have the third order missing. The third order is missing, so it means that m has to be less than or equal to 2. And so the values of m are 0, 1, and 2. And the largest m has to be m equals to 2. So once again, we had a mixed wavelength, 500 nanometers and 600 nanometers, assuming that the angle theta had to be less than or equal to 30. We wanted to solve for the slit width A and the slit separation D. We started off with the slit separation by manipulating d sine theta equals to m lambda. We had two wavelengths, a mixture, and so assuming that n was the number of lines and L is the length covered by the slits and D was the slit separation, we have n being inversely proportional to the slit separation, meaning if you increase the number of lines, you reduce the separation. The resolving power is the dispersion. So coming back to this, we see that 1 over d is a reciprocal. 1 over d is less than or equal to sine 30 over m lambda. To solve for d and to maximize d, we have to use the equal sign. We can't use the less than, because maximum separations happens when m is 2 and lambda is 600. We plug in those numbers, we get the value of d, and we move on and see that we can solve for a, since we have these two relationships, and we end up having a being 8 times 10 to the negative 7. And then finally, taking those two values, we want to maximize, we want to find where the order is maximum. Using the initial equation, d sine theta equals to m lambda, we solve for m. At maximum order, sine theta is 1, as you can see. So this value becomes 1. And then we plug in values, and we can't have 3. So we're left with the orders as being 0, 1, and 2. And so the maximum of these is 2. So I hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day.